So this topic of fractal is a very recent development in mathematics world, and when it came out and developed by a mathematician called um, Benoit Mandelbrot. It's no. When it came out, it was thought to be even at this age, 1975, it was perceived as a little crazy, a little lost touch with the world kind of crazy. Okay? This is nonsense. This is something stupid. I mean, and something non-conventional. It just goes against what mathematics has established itself for these many years. It was something totally weird and different. So at first that was perceived as very. It didn't. The whole idea didn't really pick up. No one kind of cared because it was weird. I mean, in mathematics, we love things that are mm, like totally regular. What do I mean by regular? Like, we like triangles. We like squares. We like, circles and spheres and cubes and prisms that are very regular and even straight. Okay, we deviate a little bit from, a circle to ellipse. Wow. But still so smooth and everything is so formulaic that you could, come up with all that stuff, and it is so regular, if you know what I mean by regular, right? Um, it's straight lines. I mean, that's why if you look at the architectures of our world, it is all like boxes. If you deviate from that a little bit, maybe a little bit of, a circle, maybe a little bit of an ellipse, hyperbola, maybe even some of that stuff. But we don't go beyond like a lot of these different stuff. We let the nature do its chaotic stuff, right? But when we do our stuff, it has to follow some sort of logic. We make it very formulaic because we can't deal with being out of control. Right? Anyway. So, up to this point, we have talked about dynamical system given a real function with real domain set, and we have iterated over and over again. French mathematician named, forgot the first name, Julia, Professor Julia from France. He's the one who, during World War One, posed this idea of what? Given a number, you put it through a function, given the output, you do that again. The whole what? Definition of dynamic system, right? Over function. So he's the one who first came up with this whole problem, dynamic system problem, where given a number, you go put it through a function, the output becomes a new input, you do it over and over and again, and obviously you want to see the behavior of different functions that will do what it does. We only talked about what kind of function yesterday. Mostly all what? X square functions, right? The mother functions of x squares, right? But obviously you could study that with different functions. You could study that with cubic functions, you could study that with trig functions, you could study that with radical functions and whatnot. And you wanted to do all this stuff, you want to plot all these points and see how the orbit behaves given a different seed, and we came up with, simple multiples of point ones given orbit from, where did we go from yesterday? -2 to 3 or something, right? Or in Excel, right? So all that stuff. But obviously, back in the days, they didn't even have, mathematicians didn't have access to any computers, first of all. Even if they did, it was so old and archaic that you couldn't even compute a lot of stuff. But what is one thing the computer does well? What it does is it does looping very well. It just know how to do what? Same thing over and over and over again. Repeat itself over and over again. So the computer was very necessary to further this further understanding on this topic. But obviously it was limited, so it kind of stopped. But then Mandelbrot, after he's also from France, moved to New US to work for IBM. And back in the days, IBM, they were looking to produce some sort of computers, and then they were hiring all these crazy creative thinkers in the mathematics field. Right? So he was hired because he was doing something crazy and thought it could help in doing any sort of creative mathematics. They could help to build and all this stuff. So all the dynamic systems we have studied dealt with functions, with real number systems. Right? Now I'm going to transpose the same idea in a totally different context into shapes, into geometry. But the same concept of dynamical systems still exists. You know what I'm talking about? Okay, instead of giving a numerical seed, I will give you a shape or an object. All right. So here is an example. Given the following seed, and what is the seed for our case? This line segment. All right, here's a line segment. Perform the first iteration. Okay. Oh no, here's an example of the second iteration, first iteration. And I'm asking you to follow the same function, given the seed, to create second and third iterations. So then, given this problem, you're kind of saying, Mr. Chen, okay, I understand that this is a seed, but dynamical system must accompany seed with the function. How do we describe the function? Well, given a real life polynomials, we know we square the seed and we subtract 2 or add something, right? That was a function that will give you an output. For this, what do you think the actual function in this output again? Okay, a little bit better description. A little bit better. Yeah.
Split up a straight line into thirds.
Okay, trisect the line.
Remove the middle third.
Remove the middle one.
And add 2 more lines.
2 more lines connecting. Okay, pretty good. I like that. So trisect, given a line segment, trisect the line segment, remove the middle part, and create an equilateral triangle. Could that be a good function description? Okay, and you do the same thing over and over and over and over again. Right? So that is the first description. And what else? Can we, first iteration, can we come up with a second and third? Have you tried it? Okay, so you see that the second one will, second iteration will look like something along this line. And I can tell you, after studying this topic, you will never look at what's around the scene. And this topic has that powerful understanding of how nature works and how mathematics attempts to describe nature. So it's actually almost sacred. I'm a man of faith. And I give that a lot of credit in terms of how important it is, but this is actually pretty godly. Anyway. That's on the second iteration, right? There's another one. For each line segment you see, you perform the same thing, trisect, remove the middle part, create a equilateral triangle. Alright, so let me just go on with this whole idea of performing a dynamic system upon an object or shape. Give it a triangle like this. If you perform the same function that I just did to a line segment, what kind of figures do you get? Snowflake, okay, some sort of snowflakes, meaning if I, again she says snowflake. So given this as a seed, I will come up with it's not this seed, yeah. Alright? That's the first iteration. What's my second iteration? I will then go And then you do more and more, and it looks so weird. Okay, whatever. It's called Koch's snowflake. No. Sierpinski's gas. You've probably heard this name if you follow research. What? Oh. Now, is this the same seed as the previous example? No, they're actually totally different. The triangles are the same, but one is filled in, the other one is not. Okay. So here's a filled-in triangle. What's the function? Same thing. Not same. The function is actually different. Function is what? You find the midpoint of each side of a triangle, you connect them, and you take the middle triangle out. That's the function. Okay, so if I bisect every single line, 3, and you are going to then like that. Take the middle part out. So what will be the next iteration? Now you have 3, and you and that will be the one of the iterations, right? And so forth. Do it again? Okay. Here we go. First iteration, second iteration, the third, the fourth, the fifth, the sixth, the seventh, 8th. Okay. That's just what happened. What do you see what's going on here? Now, I mentioned, if you remember before, I said there is a difference between this seed versus the seed that I showed you here. And I told you the difference between the two is one is filled in, the other was not. Right? Why are they different? What's the difference between the two? I'm doing the same function. Oh, yes, I'm talking. Yes, you're right. But I asked the seed. I asked for the seed, not for the. Yeah, why are these two different seeds? They look the same to me. They look like the same equilateral triangles. Yeah. But now you're talking about the functions of each. I'm not talking about functions. I'm just talking about seed alone. I'm telling you these two are this one versus this one is. No. But I love how you're thinking. She's talking more on the line of inverted pictures. Inverted pictures. Negative, positive, inversion of each pictures. Anyway, it's different because this is a line. More like a one-dimensional figure. It's enclosed by a line. Do you know what I'm talking about? That's still not a two-dimensional figure. It's a line. It just happens to be attached to it. Do you know what I'm talking about? Okay, it's still a one-dimensional figure, right? But this is a two-dimensional. There's a difference between the two. Okay? And when you solve this thing, if I repeat this iterations over and over and over and over again to the infinity, do you think you will end up with a one-dimensional figure? Or do you think you will come up with a two-dimensional figure? What do I mean by a one-dimensional figure? Meaning, will this be if I continue over and over, it gets smaller and smaller and smaller and smaller, will it become a small enough that it becomes a collection of points that is just connected as a complicated figure into a line. Or will it become an area, a filled-in area, so that we define it as 2? Yeah. Huh? Okay, what do you think about that? Do you think the area will approach 0 as you let n, meaning the number of iterations, approach infinity? Okay, then, okay. What do you think about that? Yes. I mean, okay. We could argue that later. But in terms of dimension I'm talking about, do you think this will somehow approach, if you let it approach infinity, a line? Segments that are just connected in all different real ways? Or will it be reason? What could it even be possible? Mm-hmm. And we are saying that we are going to the infinite amount of iterations. So in essence, it wouldn't, because it doesn't matter how infinitely many times you try, there will be a filled-in triangle, even if you what? Go infinitely many times. So it is obvious that it won't be a one-dimensional. Not obvious, but can you conclude then from that it's not going to be a one-dimensional figure? It's not going to be a line. Do you know why? Now, can you? Yeah, it's not going to be a line. So when you introduce the idea, then what does that mean? It's not going to be a line. Well, we know it's not going to what? Create a filled-in two-dimensional figure either. So what does that mean? Are we suggesting that there will be a dimension that is in between integer dimensions? 1 and 2? Wait, what do you say? If you were listening, it will make sense. Do you know what I'm talking about? Yeah. Well, as I said, it's not going to be a line comprised of all this complex ways of drawing this. My question is, using it as just single line, infinite length of line, can you possibly draw all this? And I'm saying no. Why? Because we said, well, there will be doesn't matter how many times you iterate this, there will be a triangle in this iteration. It doesn't matter how far you go in. Does that make sense? And triangle cannot be enclosed with a line. Right? So that's not possible. That means it's not a one-dimensional figure. Right? Then can you then say if it's not, then it has to be two-dimensional, right? But we have a problem with that also because it cannot be filled in. So what kind of dimension is it? Does that suggest that we have to deal with a dimension that is not an integer? No. In between 1 and 2. Don't go forward. That's crazy.
How do we get to that dimension?
So, I will come back to that. Let me show you more examples of.
Pretty true.
Yes. Here is. Can you open that window? I'm getting hot. It's getting hot.
I'm getting really excited. I'm just getting excited.
So here is a C. Let me start with a square. My function is given a square on the top portion of the square. I'm going to create a isosceles right triangle. Given that isosceles right triangle, I'm going to create squares along that side. And then I repeat that function over and over again. So given a square, here's on my top side, right? which if I define it as opposite of the one of the sides of the triangle, I construct a isosceles right triangle and create two more squares. And if I repeat that over and over and over again, just look at that picture over again. What does that look like? A tree. That looks like a broccoli too, you're right. Now, same thing, let me vary my seed. Now, let me vary my function. Let me vary my seed. Instead of having square with an isosceles right triangle, what do I have? Scalene right triangle. So one side will get bigger square than the other side, right? And then if I repeat the same thing, that will give a little bit of rotation, kind of, right? It gives that. That's a two-dimensional dynamic system of such object. Now I can turn it into 3D. Same concept. I give it a cube, right? And then you create a what? Isosceles right triangle. From it, another cube. Right? Someone actually volunteered to do this for extra credit. Yeah, construct this in a box or something. I was like, go for it. Yeah.
Oh, no, that'd be tedious.
Why are there two triangles?
I don't know if I do that.
There are two like randomly placed triangles.
Oh yeah, there are two randomly placed triangles.
Dead center on the light green.
Oh.
In between blue.
Okay. So coming back to this whole concept of dimension that's in between 1 and 2. Crazy idea. Okay, in order to to further analyze this, we need to understand what is a dimension. How do we actually define a dimension? That's more important. So how do we define a dimension? Well, we know, given a length, let's say called A, here's my length. And if I apply a scalar, meaning scaling by factor k, what does that do to that line? If I scale it, dilation. Either make it longer or small depending on what kind of factor you multiply it to, right? So if I apply that factor of, let's say, scale factor of, let's say, k, then A will become no longer A, but A times k. And it will either get longer or even shorter, depending on the value of k, correct? Okay, what if I have not just A, what if I have A times B, which will find the area? So when I have A times B and do a scaling to that of factor k, then A times k, it will be one side, and B times k will be the other side, correct? So then what's the area? It will be A, B, k squared will be the area of the new scaled by factor k squared, or rectangle. Does that make sense? What if so what am I doing right now? I'm defining a dimension. What's the dimension? So same thing with a volume, which we know is 3D. Now that I don't have AB, but now I have A, B, N, C. If I scale this A, B, C, multiply for volume by factor k, what do I get? I get A times k one side, B times k the other side, C times k, therefore the new scaled volume will be A times B times C times k to the 3. So if this is how I define my dimension, meaning here's my first dimension, this is my D. Here's my second dimension, this is my D. Here's my third dimension, this is my D by the scale factor. Okay? Now, what are we trying to do? We're trying to go between now 1 and 2, correct? That's what we're trying to do, right? We're trying to go from somewhere between 1 and 2. Well, previous Crooks snowflake. Okay, so I don't know the name of this. I don't know what the term for, it's not a line. It's not an area. I can't go. So let me just call it something. Let me call it like a size. It has no meaning. No. So if I call that size instead of volume, which will be comprised of some sort of ABC, whatever the case might be, right? Right? Let's draw a circle with something. I don't know what it is. Do you know what I'm talking about? And it has letters. So if I call that as given, let's say, size, I do the same thing. What would I do? I scale this by factor k, and what do I end up with? Size times k to the d, the dimension, which I don't know. Okay? So, once again, boys and girls, what is this? This is my new image, correct? Is this my new image after scaling my original by factor k? Right? Whether this is actually bigger than the original or smaller than the original? Right? Okay. But what is the size? In the context of area, volume, and a line, length of a line, we know the size is whatever that is, right? But if I go back to the question like this, let me just draw one here. Can I say this particular iteration right here, if I call that size, just like a square, right? So technically speaking, I should like, do you know what I'm talking about, right? All filled in, right? All filled in. So for area, this will be size, so square or rectangle, whatever. But for my context, my problem that I'm trying to solve, this is my size. And size could be at any point of the iteration. Doesn't have to be a first iteration. It could be second iteration, so forth. Doesn't really matter. What is this size? How would I? Whatever this was, which was originally a big triangle filled in, correct? And what did I do to it? I scaled it. What was the scale factor for this? What was the value of k? What was the scale factor? Well, you're talking about now. If you say that you're talking about it's in the context of the area, okay. But I'm gonna talk in terms of side length. Side length. Side length is, if that's the case, is a factor of half, right? Meaning it's shrunk, gets smaller. So then, this particular size is what? Half to the d, which I don't know. That's how this is how we're going to describe the smaller triangle, correct? Is this smaller triangle half the factor of the previous one? Does that make sense? Right. Now, if I want to describe this particular first iteration using this definition of scale factor, k, which is half, can I come up with this particular equation? Can I say this particular size right here is equal to sum of the 3 smaller triangle described this way? can I say this right here is equal to 3 times size 1/2 to the t? Now we're going somewhere because we love equations. We love equations, right? Now, what am I looking for? What am I looking for, boys and girls? D. Can I solve for D in this case? Even without knowing the size. Why? Because it will cancel it out. And that's why I say it doesn't really matter at which state of iteration you are in. Right? Because it will cancel it out. Now, what does this cancel to? 1. So 1 is equal to 3 half d. How do I solve for d? Divide this by 3. You do log, which will make this d log of half, correct? So what is d? D will equal to log of 1/3 divided by log of half. What's log of 1/3 divided by log of half? Can I write half and 1/3 as 3 to the -1 and 2 to the -1? And the exponents comes out as coefficients, which will then be still positive. So does this equal to log of 3 over log of 2? It does, right? What is it? That's my d. That's my dimension. What? What kind of dimension is that? Is it between 1 and 2? Okay, so give me the exact. It's approximately 1.58. What does that mean? 1.58. First of all, we know that 1.58 is closer to, a little bit closer to 2 than 1. That means it will be closer to 2-dimensional at least figure than 1-dimensional. But we know it's neither. Right? That is so weird. Now, does this logic work? Does this logic actually work to define known dimensions? What are the known dimensions that we know? 1, 2, or 3, right? Does this work for those? I mean, it should, right? So you know what we just did? We went from discrete of 1, 2, 3 to what now? All real. Continuous. Continuous dimension we're talking about. Now, all right, so we have, so if I look at this, 3 is, where did that 3 come from? That 3 came from number of the triangles, right? The similar smaller factor triangles, right? We multiply that by the scale, right? To get the original one. What if I change the value of d? Will that have an effect on your dimension? And someone actually asked this question in class, in my first period class, second period class, which led to a very good discussion. If I change the value of 3, will that affect my dimension? Let's say if I change this 3 to, let's say what? 4. What would happen? And I'm counting what? 1, 2, 3, 4. And graphically, that will be a 2-dimensional figure because everything is filled in. Does that actually correspond with our calculation? If that is 4, what is that? You divide it by 4. Log. What is log of 4 over log of 2? 2. That's a 2-dimensional figure. Makes sense, right? So that's how we define, hence the word fractional dimension fractal. Right? That's when we talk about a fractal being a fraction dimension. That's where it comes from. Now, perfect. So just to recap, on your homework, which you need to finish the whole dynamic system worksheet, dimension is equal to log of n. What is n? In layman's term, number of self-similar pieces from one iteration to the next. How many triangles do we see? 3 of the similar, self-similar ones from the previous iteration, right? And what is r? R is the scale factor, which was actually half for us, but we're going to reciprocal that. Do you know why we had to reciprocal that? Because we did the same thing for 1/3, right? Same thing. And that's how you calculate a fractional dimension.
So the game, we did that